The last couple nights you've learned about Lenz's law, and tonight is basically just applying the math to Lenz's law. And this unit's been kind of weird because it's mostly been conceptual stuff. There hasn't been a lot of hardcore math as in the other units, so that's kind of been a mindset shift, I think, for a lot of people. But now we are going to apply math to Lenz's law, and the math is pretty simple. So if we have a changing magnetic field through a loop of wire, you know that causes a current in the wire, and you can find the direction of the current based on what we've been doing. We can also figure out what voltage is causing that current in the wire. So if you have a current, according to Ohm's law, that current's caused by a voltage occurring across a resistor. And so, there has to be a voltage. The equation shown on the screen, which is kind of blurry, so I'll rewrite it, tells you how to find the voltage causing the current around the loop of wire. So whenever you have a changing magnetic field, that's also causing a voltage. So here's all of that in written form. Changing magnetic field causes a current in a loop of wire, which means there is a potential difference in the wire. And this formula gives that potential difference. I'll rewrite it because it was kind of sloppy. Curly E for EMF. So EMF, or the voltage caused by the changing current, is the number of loops in the conductor, or in the wire. And for most of our examples, we will just be using one loop. So in our examples, usually n equals 1. Number of loops in the conductor times the change in the magnetic flux, sometimes called phi b, sometimes called phi m, divided by the change in time it took for the magnetic flux to change. So how much the flux changed divided by how much time it took times the number of loops in our wire. And like I said, usually for our examples we'll just use one loop. Pause and copy that formula, and then we will move forward. So here's our first example. A rectangular loop with dimensions 0.1 meter times 0.2 meters is in a 10 Tesla magnetic field pointed into the page. So whenever you see this, it gets confusing if you don't draw it. So I'm going to draw what it tells me there is. It says I have a rectangular loop of wire inside a magnetic field that's pointed into the page. So then I have this magnetic field pointed into the page. The field is then turned off over a period of 2 seconds. Find A, the direction of induced current, and B, the induced EMF. So first, we want the direction of the induced current, A. For this, we'll need to use the right-hand rule. I'm not going to do it on screen because those videos tend to mess up when I try to do that. We have a field into the page that is decreasing. That loop, due to the principles of inertia, does not want that field to change. So it will generate a field into the page to try to keep the situation from changing. So we're taking away a field into the page, meaning the loop is going to make a field into the page. So if we zoom in kind of inside that loop is generating a current. So that's the current from the loop. Sorry, not current. That's the magnetic field that the loop is generating. In order to make it into the page, so if you point your thumb into the page, my fingers are curling around clockwise, so that means there's an induced current kind of going in that direction. So our answer would be clockwise around the loop, kind of that way, for our induced current. Now I want to know the induced EMF. Well, I just gave you the formula for the induced EMF. By the way, EMF, if you don't remember, means electromotive force. It is not actually a force, it is a voltage. It compels electrons to move from one side to the other. That's why we refer to it like a force, but it's actually a voltage. So we'll have E equals number of loops times change in phi divided by the change in time. Okay, so this is just a single rectangular loop, since it says a rectangular loop, so n equals 1. But we don't know phi. We know the field is 10 Teslas, but we don't know the flux through that loop. Remember, phi is flux. So first, I need to find the flux through that loop at the beginning of the situation. So my initial phi, if you remember from a couple days ago, should just be the field times the area, and there's no angle between them, but if there were, it'd be times sine theta. And my field is 10 Teslas. My area, since this is a rectangle, would just be 0.1 times 0.2 meters, 0.1 meters. times 0.2 meters. And if you carry out that math, I get that my initial flux is 0.2 Webers. So that's the initial flux. The problem says that we're going to turn off the field. The field is turned off. So that means our final flux is 0. And the reason I wrote that is because, remember, anything with a delta contains final and initial. So phi b, or delta phi b, is equal to phi bf minus phi bi. Okay? And then I'm also going to need the change in time, delta t, which was 2 seconds. So it looks like I'm ready to solve this now. So if I bring this equation kind of down here, I have one loop, so EMF equals one loop times 0 minus 0.2 Webers, final minus initial, or you could just recognize that the change is 0.2 Webers, divided by 2 seconds. And my voltage then, or my EMF, is, I'm going to get 0.1 volts, and it'll be negative based on what I just did. But remember, in physics, negatives and positives indicate direction, and we took care of direction up here when we were using the right-hand rule. So I'm just going to say that my electromotive force is 0.1 volts and leave the direction to part A. Also, unless you're specifically asked on the AP exam for a negative or positive in your voltage, they're not going to count off for keeping a negative or putting one in this case. And so either answer would be acceptable. It's just cleaner to leave it as 0.1 volts and let the right-hand rule deal with direction. Pause if you need to, and then I'm going to move on to the next example. From that example, let me say, remember to, as Nike says, just draw it. Wait, that's not what Nike says. But either way, you should just draw it. Anytime you're given a problem with magnetic fields, draw what's happening. You've had on quizzes where people tried to do them without drawing it, and they got really confused. Don't be afraid to draw things. When some information is given to you about a magnetic field, draw what's happening. Otherwise, you're going to get confused because it's too much to keep track of in your head. Just draw it. All right, example 2. A circular loop with diameter 0.5 meters and resistance of 20 ohms is pushed into a 1 Tesla magnetic field pointed out of the page. Okay, so draw it. Our field is pointed out of the page. Notice that I just took 15 seconds of your time to draw that because drawing it's important. And our loop is being pushed into the page. So here's our loop. And it's being pushed that way into the page. So a velocity that way. Takes 1 second to move into the field. Find the direction of the induced current. So we're increasing the flux out of the page in that loop, which means it doesn't like that. Its inertia doesn't want there to be a flux out of the page. And I'm going to say cancel. I know I told you not to say fields cancel, but I don't have a better word here. In fact, I was thinking about it before making the video, and I don't have a better word. But because the field doesn't want there to be a flux, a new flux out of the page, remember, we don't like change, that loop is going to create a field into the page to try to cancel the flux that's being added to it. Now, this only works with changes. If we just had a loop sitting in that field, nothing would be happening. So once the loop's in there, it's done, the change has happened. But as it's happening, that loop is kicking and streaming and saying, no, I do not want there to be a field out of the page. There wasn't one before, and I don't like change. So I'm going to make this field into the page to try to cancel out the one out of the page. And so now if we take our thumb and we check it, point into the page, my fingers curl around clockwise, and so that means we have a current induced clockwise. So for part A, CW is fine for clockwise, and if you were to do counterclockwise, it's CCW. You'll see that in a lot of physics texts and on the AP exams. So no, CW means clockwise, CCW means counterclockwise. And so my current goes like this. I also draw the picture just so everybody knows what I'm talking about. Next, I want to know the induced EMF. So to find induced EMF, we have a handy-dandy formula. Induced EMF is number of loops times change in the magnetic flux divided by the time it took to make the change. Okay? So, number of loops, it's a circular loop, so n equals 1. We've got that. With a diameter of 0.5 meters, probably going to use that to find area because my flux, my initial flux, would just be the initial field times the area, and there's no angle there. That should be an A area. So that means I've got 1 Tesla. It's my initial field, what we started with. This is a circle. Area of a circle, so area for a circle is pi r squared. So pi, diameter is already in the right units, 0.5 meters squared. And that should give us the initial flux. So if I carry out that multiplication, I used 3.14 for pi, and I got 0.79 Webers with some rounding. So around there, you could have gotten something different. That's our initial flux, and oh wait, no, that's our final flux. So this is a good mistake to point out. The field was not in the loop. So it tells us that our loop started outside the field. So that means our initial flux was 0, and this is our final flux because we end up pushed into the field because we're pushing it into the field. So my mistake there was I treated it like the loop started in the field and was taken out, but it actually starts outside the field, so initial flux of 0, and goes in. And so now I'm ready to do my EMF equation. The EMF is 1 loop. You could write the unit to loops, but n is just a number, and so I don't have any units on it. That delta phi b contains, remember delta contains final minus initial. So my final is 0.79 Webers minus my initial, which is 0. And again, you can just realize, oh, the change is 0.79 and plug that in. And it says it took us 1 second to do that. Well, this looks easy. 0.79 minus 0 will be 0.79, times 1 is still 0.79, divided by 1 is still 0.79, so 0.79 volts is my induced voltage, my induced EMF. And remember, EMF is voltage. Now the question could be confusing, and I'm going to color code this next part. Find the magnitude of the induced current. That could be confusing. How do I do that? Well, I have a voltage. Remember that E is just a voltage. And that can be confusing. Like, having it as E might mess you up, but E is the formal symbol for EMF, so we've got to use the E there. But it's just a voltage. The problem gives me a resistance. That means I have a voltage and a resistance, which are related to each other by Ohm's law. I'm asked to find a current, so Ohm's law has everything I need. I've got my voltage, I've got my resistance, I'm looking for current. So now I just solve for I, V over R equals I, and I substitute in. 0.79 volts divided by 20 ohms gives me a current of about 0.04 amps. Just some rounding there, so you might have gotten something a little different. But that's what I do. You're going to be asked questions like that. And if you didn't watch this video, they'll be really confusing. But that E can be tricky. Remember, E is just a voltage. And so once you've found E, you've got a volt that can be used in any equation with voltage. We could find power, P equals IV, P equals I squared R. It's just a voltage. It can be used in any equation. So don't forget the old stuff. This all links in. There's one special case that shows up a lot on the AP exam, and that's a rectangular loop moving in or out of a magnetic field at a constant speed. What I'm about to show you requires all these things. Your loop must be a rectangle. It has to be moving in or out of the magnetic field, so it can't be moving like parallel to it, and it must be at a constant speed. It can't be accelerating. The hardest one there that's going to trip people up is that it must be a rectangle. If this is a circular loop, the rule I'm showing you does not apply. You could, if you were given the speed, you could figure out how long the loop takes to get out, because you could say, oh, well, the loop is this big, and if it's moving at this speed, it must take this many seconds, just by using d equals st, distance equals speed times time. So you could do that, and then sub it all in to E equals n delta phi over delta t. But there's a lot simpler way, and in fact you would end up with the same answer if you did it this way. If you have a rectangular loop moving in or out of the magnetic field at a constant speed, the formula for the induced EMF is E equals BLV. B is the magnetic field. L is the length of the wire perpendicular to the velocity. So notice this length, because over here is my velocity, and they are perpendicular. The length perpendicular has to be the perpendicular length to the velocity. So notice this length up on top would be parallel to the velocity, because our velocity is shown to be that way. Those are parallel. It's the length perpendicular, so perpendicular to velocity, magnetic field times the velocity. It's very simple. So anytime you're given a rectangular loop moving in or out of magnetic field at a constant speed, all you do is throw those numbers together, E equals BLV, and you've got it. Now then, of course, you can use that E as the V in Ohm's law, or the V in the power equation, but that's all you do. Magnetic field times length times velocity. If you would like to convince yourself that that's right by maybe making up an example or trying just the picture up here using these equations and see that you get the same thing, you can. But for this level, last thing we're learning, it's sufficient to memorize for a rectangular loop moving in or out of the magnetic field at a constant speed, use E equals BLV, where L is the perpendicular length to the velocity. And that's all. Have a good night.